All right. Again, my name is Mathew Rowley. This talk is called Debuggers Are Really Powerful, Owning All the Android Things. Again, so I'm a senior security consultant at Mathew Security. A little bit of background about myself, why you should listen to what I have to say. I manage the research for Mathew. My Twitter is 1T, and GitHub is GitHub/1T, which will, any code that I show on this will be up there later. A lot of people ask me what 1T actually means, and it's a kind of a play on words, because my name is spelled Mathew with 1T. Get it? So what's this talk about? I have been looking at Android applications for a long time and finding other ways of reverse engineering them. Easier ways. I see Android applications all the time when doing my job. So I found out that there's a lot the debugger that Java allows you to use is very, very powerful, and I found out that there's a lot that you can do with it that will help you in reverse engineering applications. So, what this talk is about is how to utilize that debugger when reverse engineering Android applications, when you don't have the source or when something's very obfuscated, and just simplifying ways of reverse engineering Android applications. It's also about the Java debug interface, specifically the implementation that Android does, the JDWP, which stands for Java Debug Wire Protocol. I also developed a scriptable debugging framework that's written in Ruby that helps facilitate a lot of the process and a lot of the techniques that I'm going to be talking about. I also developed a set of tools that is written on top of this debugger that will allow you to use the debugging framework without knowing much about it. So who should listen to this talk? If you're curious about Android applications at all and how the debugging process works behind them, you should listen to this. If you're curious about JDWP in general in Java and specific to the Android implementation, you'll gain some knowledge from it. If you want to be able to take advantage of Android apps in general, just from a simple script and running, I see it as kind of like a proxy that your application runs over. And then if you understand the benefits of scriptable debuggers, I had always not understood that in the native code sense, but now after doing this project and looking at them deeper, I completely understand why and how they're helpful. So a little bit of background on JDWP and just the debug interface that exists in Java. There are three different concepts to understand: the JDI, which is the Java Debug Interface, JDWP, which is the Java Debug Wire Protocol, and then the JVM TI, which stands for Java Virtual Machine Tool Interface. In the Android implementation, the layout is how it is shown at the bottom. You've got the debugger, which is like Eclipse or like this debug framework that I'm going to show later. It calls API calls that are implemented in the Java SDK that runs on your machine. And this, from what I've seen, the only thing that actually implements these APIs is the Oracle Java interface, or Oracle Java SDK. And then that communicates over, in the Android sense, over TCP, using the Java Debug Wire Protocol to the JVM TI, which is what's implemented on the JVM that's running the application that you are debugging. So every application that runs on an Android device is running under a JVM. That JVM can or cannot implement remote debugging, and Android it obviously does, because that's how you develop Android applications or debug Android applications when you're developing them. In general, there's three different types of connections you can use when initiating a JDWP or Java debug session. There's the command line launch, which is as it's the name says. You just, whatever you would run java-jar and then whatever the command line arguments are, you can do the same exact thing with this specific type of connection. There's also a process attached, so any process that's already running, you can attach to it, just like GDB has the ability to attach to a PID that's already running. And finally, a socket attached, which is how Android applications are debugged, which actually communicates over TCP to the NJVM from the JDK that you're developing against. So this is what we're going to talk about, and this is what we're going to use for the Android-specific stuff. So when I first started looking at this, I was developing a lot of the software in Java, and this code snippet is what you need in Java to initiate a socket connection. It's very convoluted. It makes absolutely no sense. You have to first get the list of connectors from the virtual machine, from your local virtual machine, see if any of them equal the one that you want, and then from there, pull the arguments from that object, find the names of them that you want, change those argument values, and then replace them back in the object. It seems like it's kind of going counterintuitive to the whole object-oriented language. Like, why couldn't I just create the original object and then set the arguments to it? I have no idea, but this is how it's done. If anyone wants to develop in Java, I simplify this later in Ruby. So when I saw that, this is exactly how I felt. I was like, why? I don't know. I guess the Java developers didn't want to spend much time developing that. But anyways, yeah. So when developing and trying to learn programming JDWP and the whole Java, programming against the Java interface, there's not much out there to look at and to reference. So there's lots of documentation on it, but the documentation is mostly about how you would implement a JVM TI. So like if I was developing a Java virtual machine and I wanted to have the debug interface available on that and be according to spec, that's what all the documentation is about. And on top of that, there's just the API docs, which those are the two links to that there. And there's nowhere that I found has any code that's developed against this, except for 3 specific applications that exist in tools.jar. The trace, JDB, and Java DT, which is the start of a Java debug GUI. What I found actually was the best reference for information was the test cases that Eclipse uses when it builds. Eclipse obviously has a full interactive debugger that does everything that I would ever want to do, but these test cases show exactly how this stuff is supposed to be used and shows how they developed it, which was very helpful. So typically when I think about a debugger, this is what I see in my mind, something that's very, very low level that I access core memory directly, and that setting a breakpoint is actually modifying the application's bytecode. When in Java, you have to realize that Java is an interpretive language. So the debugger the debugger is built on top of Java. So I think of it as kind of like the Java debugger is like an object-oriented debugger. It has the concepts of objects already built into it. You can call methods on objects that are already there. So you can't think of the Java debugger as a normal debugger. It's an interpretive language debugger, which gives it a whole lot more powerful, which makes it a whole lot more powerful and gives you the ability to do a lot more with whatever you want when you're debugging. In comparison, a native debugger it accesses raw memory, just like the immunity debugger, GDB. It's changing things in memory and telling your processor that this should be a breakpoint, or execution should stop here and it should listen to wait for what the debugger should do next. In Java, this is, it's one layer up. So there's this whole JVM layer that exists on top of the raw memory. So yeah, you could debug the Java virtual machine that's running your Java bytecode, but the Java debugger provides you with all these additional tools that you can take advantage of that you wouldn't need to do that. So some of the things and the helper functions that the Java debug interface provides for you are they want to understand what an object is. You can pull an object from the remote process that you're debugging into your scriptable debugger, muck with it, and it changes it directly in the application. So you can call it. You can also call and invoke methods on those objects. So, for example, there's a client-side authorization, and there's a function called isAdmin. You can have that always return true, for example. You also have access to this method. So this object, when you're debugging, you set a breakpoint in a specific place, and you do that by saying set a breakpoint on this anytime this object is called, or anytime any method under this object is called, and then from there you have an instance of that object. So being able to access this, you can set like a variable that says isAdmin. You can set that directly to true. In general, the Java debug interface also has the ability to view the raw Java bytecode for where you actually are, which unfortunately isn't implemented in Android, but I think would be a really cool feature to look at things at a lower level than objects. For the Android-specific TI implementation, which is which in the Java the Java instance that's running on the Android device, they have this interface that takes in all these packets that have JDWP information in it. It doesn't implement all of the JDWP operations that are available, and there's no documentation for what it does and what it does not implement. So what I had to do is actually go through to the Android source and find where in the Dalvik virtual machine it actually deals with all this stuff. So this class, the JDWP handler, is what takes in the incoming packets and will pass along the functionality to wherever it needs to go. It has a huge array, huge array of what classes are implemented and what are not implemented. The reason I had to end up finding that was because the first time I was developing this, developing an application to integrate or to interact with this stuff, I noticed that the Java app, the Android application was crashing hard. Like the full JVM was crashing. It was doing a stack trace in logcat, and I had no idea why. I thought there was a vulnerability somewhere that I couldn't find. But that's what I found out later was that the Android JVM crashes hard when you call a debug method that doesn't exist. So when you communicate with an Android application, during development or during reverse engineering or anything, you usually go over, you use ADB, which communicates to, which stands for Android Debug Bridge. And it comes in the SDK, as anyone who's looked at an Android application knows. But at a lower level, it also spawns what's called a running process that's listening on a remote port, or on a local port 5037 called ADB server. ADB server is what actually does all the magic. That's what figures out if if you want to communicate to a device, are you communicating with one over the USB port, or are you communicating with one that's running as an emulator? How do you interact with it? And that just has a simple binary protocol. The ADB executable just basically sends simple packets over port 5037 to tell ADB server what it wants to do. So when you initialize a debug session with a running application, you have to communicate over this Java debug bridge, because that's what facilitates communication between a debugger and the actual application. Because like I was talking about before, we use the socket connector to actually connect to it. So this is at a lower level of exactly how this all works from an Android perspective when you're initiating a debug session. So first, all of the communication happens over ADB server over port 5037. You first have to understand which application you want to debug, so you have to list all the applications. Then you tell the Android operating system, I want to debug this application. The Android operating system then flags that application next time it's going to launch, it's going to wait for a debugger before it launches. You then launch the application. Then you have to get the PIDs that are associated with Java debug wire protocol or that are waiting for a debugger. And then you have to tell the Android operating system to forward the port that is listening on over to your local host, and then ADB will open up a port that you can connect the remote Java debugger to, and from there you can start communicating the Java debug wire protocol directly to the application. So this long process is all handled typically with DDMS and the tools that come with the SDK, but I wanted to reverse it and figure out so I could write it natively and not have to rely on those libraries. So we'll talk about a little why did I start looking at this stuff? Why did I start this project? So anytime I look at an application that's very obfuscated, it looks like this on the left, and I feel like, watch it one more time. I feel like this guy on the right. I'm like, you're just making my life more difficult. It's security by obscurity. It's never going to be successful, but that's why I originally started. The specific problem for the application that I was looking at was it was obviously very obfuscated. The Android client communicated over SSL to a server. It also doubly encrypted the data with AES, so it was SSL and then AES. And I thought this was very stupid. But then now, seeing with the NSA crypto leaks, which actually doesn't even make sense because apparently AES is broken. But yeah, it's not so dumb anymore, is what the point I was trying to make. So the first step to getting into the middle of this protocol was to man in the middle of the SSL communication, which was easy. You can use Burp, you can use whatever tool you want. But then I had this second problem was there's a doubly, so now I just have this encrypted AES blob. How do I know what that actually means? And this application was very, very obfuscated. So kind of trying to think outside of the box and how to get to, my goal was decrypt this data. How do I get that the fastest? I thought a debugger may be helpful. So I decompiled the application using dex2jar and JDGUI, and I started associating it with Eclipse. And this is a video of all the steps that it's going to take to actually do that. I did a talk last year about reverse engineering Android applications. And you assume that you don't have the source of the application. So the first thing you need to do is decompile it, and then save the source from JDGUI. From there, it saves in a zip file, so you have to unzip it. And then in Eclipse, so I'm going to use Eclipse as my debugger instead of a scriptable debugger. You have to create a new project, and then you import the source that you just created from that zip file, the source that you decompiled into the Eclipse project. And the only reason that you're doing this is because that source knows all of the methods. So as anyone who's looked at Android applications knows, it's not a one-to-one decompilation. So this source isn't going to compile, but I don't need the source to compile. All I want to do is look at the methods, because I can do breakpoints on methods instead of specific code lines. So I'm trying to get what the return value is of that string in this application. So I set a breakpoint on the entry and exit of that method. And so when I run the application after it's attached to the debugger, I can hopefully see the variables that are in there. So what I'm showing right there is what I want is that return string, because that's, in this specific application, the password function. So in the old Android versions, there was a helper application in DevTools that allowed you to select an application and make sure that it make sure that it waits for you to start. Okay, why not? We're doing shots. Yes. What? Now we can do a big one. A big one? We can do a little more. There we go. Cheers. No, I'm good. Woo! All right. All right. Now I'm confused. Did he just want me to take a shot, or was my talk getting boring? I don't know. Okay. Good to go. Should have brought a beer with me. So the problems with this technique were that I don't even know what I'm talking about anymore. All right, let's get back in the game here. The problems with the technique is that it's not very efficient. You have to decompile the code, import it into a project. You don't know where you're going to break. There's nothing fun about it, and all I'm really getting is a decryption key. Finally, the stepping isn't even aligned properly. So the source code, when you step through it, if I would have let the video keep going, which I don't think I should have, it shows that the stepping through it doesn't align properly with the code. So the line numbers don't exist properly. So I originally wrote these two applications called JavaTap and CryptoTap that are in my GitHub page that use Java to do exactly this programmatically. CryptoTap, all it does is breakpoints on the java.crypto.cipher methods, and it'll print the decryption key or the decrypted blob out to standard out. And then JavaTap is kind of a general use case for that you have a configuration file where you specify the methods that you want to break on, and if you want to break on the entry or exit. And this is what I developed that would cause the Android applications to crash hard. So the JVM was actually crashing. And but this is like step one of the framework that I did develop. So all this source code, if you ever want to develop debug libraries that use JDI interface, this is a good place to start. It gives you a little bit more insight other than the Eclipse stuff and the stuff that was provided to you directly from Java or from Oracle. So these are all means to an end for me. So I'm doing this just to get that decryption library. So after this, I gave up. I didn't really care. I was able to get what I needed out of this one project. Then I went to I started another project that recently that had a lot of broadcast receivers. And broadcast receivers are one thing that people that I see that people don't tend to look at when reverse engineering or when assessing Android applications. And in the Android docs, it says, the developer docs, it says this: when you use register receivers, any application may send broadcast to the registered receiver, which made a lot of sense to me, because if I can send the receiver something before it happened, then I can potentially end up in a race condition. So I needed to be able to detect these within this large application reliably. And you don't have to register these in the Android manifest anywhere like other IPC mechanisms. These just exist. They're dynamically created throughout the code while you're developing the application, or while the application's running. In this specific case, there's a download manager that uses broadcast receivers, and what it does is you can send the download manager and tell it to start downloading a file, and when it's done downloading, it'll send back a broadcast message saying that this file has been done downloading. The correct way of doing things is to query the download manager's database to find out where the file actually exists, but for some reason this application made its own custom download manager. And what it did was, when you initiated download, so the whole function, the reason that this existed in the application was to do live updates of the lib directory in the application. So the custom download manager downloaded a file, and then then you register a receiver, and then when the file is done downloading, it sends it sends a broadcast message saying that this file is done downloading. But in the intent that was being sent for that broadcast, it also included the name of the file. So what would happen was the application would copy that temporary file into its local lib directory and override the previous one. So what I found with this specific case was that if I could find out where this is happening, I could send the broadcast, when it's trying to download a file, if I can send a broadcast before it got the broadcast from the correct download manager, I can essentially update files to something that I own. This obviously has to be running on the application or on the Android device, but it's essentially remote code execution in another Android application. And this is when I started developing Android Debug. Android Debug is a scriptable debugging framework written in Ruby. That shot is killing me. It's a scriptable debugging framework written in Ruby. It has to run over JRuby, and it's gemified. I haven't submitted it to any Ruby gems or anything because I don't know if it was written properly. I've never written a Ruby gem before, and I'm a little scared that they're going to yell at me if I do something wrong. But it exists. You can build the gem locally. It's got full documentation with it as well. It requires Oracle Java because that's the only one that implements the JDI interface, the API calls that you need to call. And it has, essentially you just call one method and it launches an application, attaches a debugger to it, and you don't have to deal with any of that garbage that was shown in the video. Some of the key concepts that exist in this that have the helper functionality that is built on top of the core JDI interface are the ability to read variables, the ability to write variables, the ability to call arbitrary methods during a breakpoint, and you can programmatically step through the application to get to essentially wherever you want. So I see this scriptable debugger as kind of like a proxy to an Android application. When you're man-in-the-middling traffic, you actively man-in-the-middling it, you can modify the traffic before it hits the endpoint. And it's very, very similar concept. You can modify the flow and how the application actually works while it's running. It blew my mind when I saw that all this stuff was able to be done. So the initial framework ideas and why I actually developed it was intents are kind of like a mystery. I know that I can communicate with receivers via intents, but the intent has to be created properly to get to the receiver. In an obfuscated application, how do you know how that intent was actually created? Because intent is just like a key value store. So if I'm able to attach to every time an intent is created and anytime it's manipulated, I can essentially dynamically build what the intent looks like prior to it being sent to whatever receiver it's going to. And it's, again, specifically for this broadcast receiver, it was very, very important. The other way is thinking about obfuscation differently. A lot of people look at an application that's obfuscated and have to like sift through the code to try to figure out exactly where they are they want to get to. But if you think about what your end goal is when you're looking at an application, you don't have to even think about obfuscation if you're using this debug interface. So for example, the last application that had SSL over, had AES encryption over SSL, my goal was just to get that private key so I could decrypt the traffic. I didn't have to deal with any of the obfuscated code because the core Android operating system libraries are not obfuscated. If you can think that like far in advance, you can break on those and then never have to deal with the obfuscation ever. So this is a sample code for a hit tracer using the library, the framework that I created. The first line just, it attaches and launches the specific application. You then just add a breakpoint. And then anytime it hits that breakpoint, it'll run that on break code. And in this case, it adds one to a hash and then prints out the current status. This would take hundreds of lines of Java to do. In the framework, there's three different major types of classes. There's a Java pass-through class, which is a Ruby class that extends one of the core Java JDI classes. Anytime you have one of those objects, you can simply call a method on it, and if it's not implemented in the Java library or the Ruby library that I created, it will pass it through to call it on the core Java library. There's invocable, which will, any object that you pull in from the remote debugger into your application, and you can invoke methods on it, will extend this, and you simply can, like if you pull in a string object into your scriptable debugging script, and you just call like .toString, which is a common Java method, it will call that in the context of the application running on the remote device, which is still blows my mind that they have this actually available. And then there's a bunch of helper classes that like do things like launch the debugger, communicate over ADB, and tunnel traffic, that type of stuff. These are the specific pass-through classes that exist: event, frame, local variable, and object and frame. Again, anything you call on those will pass through all the way through to Oracle Java. So the methods that exist on those classes you can access directly from Ruby. Invocable, which is these two variables, are this like the this object, or if you set a breakpoint and you see what you can say, what are the variables that exist at this breakpoint? Pull in one of those objects to your application, and you can call any method on that object that you want. That's what local variable is. And then the helper functions. The debugger is where you're going to interact with the remote interface or the remote application the most. The JPDA, which is helper functions for the communication that the JPDA protocol. ADB, which helps, which communicates over the Android debug bridge using the ADB executable, and the ADB native, which is kind of still in development. I'm just not fully trusting of it, but communicates over ADB using raw TCP. So you don't really need the native libraries. When using this, there's a couple nuances. You have to use the Oracle Java, obviously, as I explained a couple times, because Oracle Java is the only one that implements these classes. Also, when you set a breakpoint and you're doing something on that breakpoint, all of the variables have to be accessed from that raw debugger object, or the core debugger object that you created. That's due to stepping. So if I do a step, it doesn't resume the virtual machine. It'll step, and then the next line of code in your Ruby application will execute. But I can't update the variables you already pulled from it, so it kind of becomes a pain. In Linux specifically, you have to use the Oracle JDK, not the Open JDK. And some people told me that they had to explicitly include the tools.jar to the class path. The tools.jar is what contains all this JDI API stuff. I don't know why, but I don't really use Linux much. And then calling methods is kind of funky. You can only call one method when you're actually at a breakpoint, but if you just set a breakpoint at the next step, then you can call multiple methods. But you can potentially get into this infinite loop that if your breakpoint, if you call a breakpoint in the step and that triggers another breakpoint, you get into this infinite loop where you can never resume the application. That's just like a nuance from the JDI Java ABIs anyways. Some of the templates that I wrote that already exist in applications that already exist in the library are, there's a template to invoke a method, so it'll show you exactly how you can invoke a method. There's a template for single stepping. There's a template for changing variables, and then the hit tracer. What is going on the stage up here? What was that? I don't know. Then there's a hit tracer, and then a way to print variables during the breakpoint. My hopes for the future development of Android's Java debug interface is that they implement the bytecode functionality, and then they don't have a way to explicitly call exit breakpoints. You have to do kind of a trick, and that they don't hard crash when you call methods that don't exist. So the conclusion of all this stuff and doing this development was that the Java debugger can act as an application proxy. You can cause an application to operate in any way you want it to very, very easily using this debug interface. You can use the Android debugger to change the code of applications, and if you can think about things in a different way, you can bypass the obfuscation of the application. So Android debug is kind of in a usable state for me. I don't really plan on doing much more development. If anyone has any requests for additional features or additional functionality, I actually just had a bug fix come in today. And if anyone wants to contribute, feel free to pull it off my GitHub. And there's another idea that I'm not sure if that I'm going to implement in Android debug, but kind of taking this a step lower, having the ability to attach to a process using ptrace, and then programmatically modify the core JVM memory. So you can do things like attach to processes via a debugger that you shouldn't be able to attach to. A complete side thought that I was thinking about today, actually, that I wanted to just bring up, because this is some research that I'm not going to do, but I think could be very fruitful. So I first started thinking about this when I thought there was a vulnerability when the Java applications were crashing hard when I was calling the wrong functions. But what happens is the debugger D will look at the application, the raw memory of the application when it crashes, and figure out why it crashes and print out the stack trace. You can also intentionally crash an Android application pretty easily just by adding some native code that does something it shouldn't do. And you also have full control of your JVM's memory. So similar to how, like, if you have a executable and you open it up in IDA Pro and it initiates an exploit that crashes IDA Pro, I was thinking that it could be possible to use that same kind of concept and muck with the JVM's memory, then cause it to crash, and then exploit debugger D or whatever else examines the process, because all that stuff runs as root, and that would be cool. So that's kind of a give me. Anyone wants to look at it? I think it's interesting. And that's it. Again, my name is Mathew Rowley. This is my Twitter. If anyone needs to contact me, my email, and all this code is up on GitHub. Thank you.